Hello again. This is Math 2233 coming to you from the College of DuPage. The title of this lecture is Cylindrical Coordinates and Triple Integrals. As always, please be an active learner as you watch this video. Triple integrals in cylindrical coordinates. By way of introduction, in plane geometry, the polar coordinate system is used to give a convenient description of certain curves and regions. And you remember also that it enabled us to more easily do some integrals, and the connection between polar and Cartesian coordinates is as follows. If the point has Cartesian coordinates xy and polar coordinates r theta, then from the figure, and so here you have a point, this could be called xy or r theta, but x and y, because of the Pythagorean relationships that exist in this right triangle, are that x is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared, and the tangent of theta is equal to y over x. In 3 dimensions, there is a coordinate system called cylindrical coordinates that is similar to polar coordinates and gives a convenient description of some commonly occurring surfaces and solids. As we will see, some triple integrals are much easier to evaluate in cylindrical coordinates. Cylindrical coordinates. In the cylindrical coordinate system, a point P in 3-dimensional space, you can see it here in the figure, is represented by the ordered triple r, theta, and z. So this point is r, theta, and z, where r and theta are the polar coordinates of the projection of P onto the xy plane. So if we project P onto the xy plane, we get this point where z is equal to 0. But you can see I can change this, the x and y of this into polar coordinates r and theta. So r and theta are the polar coordinates, the projection of P onto the xy plane, and z is the directed distance from the xy plane to P. So z is actually what it always was. So to convert from cylindrical to rectangular coordinates, we'll use these equations. X is r cosine theta, y is r sine theta, and z is z. Whereas to convert from rectangular to cylindrical coordinates, we use r squared equals x squared plus y squared, tangent theta equals y over x, and z equals z. Now here's an example for you to consider. Plot the point with cylindrical coordinates 2 pi over 3, 1, and find its rectangular coordinates. And part B, find cylindrical coordinates for the point with rectangular coordinates 3, minus 3, and minus 7. You know what to do. Let's see how you did. All right, so to plot this point, you realize that you're going out 2 in the radial direction, and you're going from the positive x-axis, going what I'm going to call counterclockwise, 2 pi over 3. So that's what you have, and then you go up 1. And so you go up 1. Now, so that's where the point is, and we used cylindrical coordinates to plot it. But we also wanted to find the coordinates. So you see, x is going to be r cosine theta, so it is 2 cosine 2 pi over 3. I expect you to be able to do this without calculators and do it exactly, but we will get minus 1 for that. Y is going to be r sine theta. We plug in the numbers and we get this, and z is equal to 1. So the rectangular coordinates x, y, z are going to be minus 1, square root of 3, and 1. For the second one, you're finding just the cylindrical coordinates for this, so we use the reverse transform, And so we find that this is 3 minus 7. So r is the square root, principal square root of x squared plus y squared, which is, when you simplify this, this is going to be the square root of 18, which is 9 square root of 2. You can pull the 2 out. So it's 3 square root of 2. The tangent of theta is equal to minus 3. That's the y coordinate, divided by x is minus 1. And when the tangent of theta is equal to minus 1 in our domain, and there's many different ways you could express this, but we're going to call it 7 pi over 4. That's the simplest thing that we can get for that. And plus, and then you could be 2n pi. And z, of course, is just minus 7. So again, you could plot that as well. Cylindrical coordinates are useful in problems that involve symmetry about an axis. And in these examples, the z-axis is chosen to coincide with the axis of symmetry. Clearly, you could have other axes of symmetry and just address things by translations and rotations. For instance, the axis of the circular cylinder with Cartesian coordinates x squared plus y squared plus x squared plus y squared is equal to c squared is the z-axis because there's no z. So z could run across anything, and x squared plus y squared equals c squared is a circle of radius c, so the cross-section is always that. Now, if you think about this in terms of cylindrical coordinates, we have x squared plus y squared equals c squared. That means r squared is equal to c. That means r is equal to the absolute value of c. So in cylindrical coordinates, this would be r is equal to a constant. Here's a problem for us to deal with then. We're to describe the surface whose equation in cylindrical coordinates is z equal r. You know what to do. Let's see how you did. So since z equals r, we can square both sides, and we get z squared is equal to r squared, and that's equal to x squared plus y squared. Now we recognize this, and we studied this earlier in the course, is a circular cone whose axis is the z-axis, and here's the picture. And so z equal r is a cone. So let's evaluate a triple integral with cylindrical coordinates. So suppose that E is a type 1 region, and so here is E, it is shown in blue, whose projection D onto the xy plane, so this is the projection onto D on the xy plane, but the projection D, if you look at this, you have it's actually very convenient to describe this in terms of polar coordinates, and probably awkward to do it otherwise. So what we have is theta is running from alpha to beta, and r is running from h1 of theta to h2 of theta. Okay, so that's the geometrical situation. So previously then, we would have a triple integral, the triple integral over E of f of x, y, and z dv would be, and we would integrate first with respect to z, and we would go from u1 of xy to u2 of xy, and then we would have dA, this is dx and dy, and we would work with that. But since we're in this situation, we will have that integral is equal to, and so we're going to have dz is the first integral that we'll have, but we're going to have to change u1 and u2 from the representation of x and y to being r cosine theta and r sine theta. So we integrate with respect to that first. Then we're going to integrate with respect to r. But remember, in polar coordinates, dA becomes r dr d theta. And so we have another factor of r there. And our function f also is no longer x, y, and z. I still have z here, but it is r cosine theta and r sine theta. So this is the expression that we get for that after we do that conversion. Okay, so you want to remember then that the volume element in cylindrical requirements is this, and we reviewed that. So dV is r dz dr d theta, and now we have a problem for you to do. I will read it for you. A solid E lies within the cylinder, x squared plus y squared equal 1, and below the plane z equal 4. I did draw a picture here for you, but you don't necessarily have to draw this picture. You can sketch it yourself. And above the paraboloid, z equal 1 minus x squared minus y squared, and that's this paraboloid here. So you see the bottom of this is not flat, but it is curved because you're above that. And we're also making this into a density problem as well. So the density at any point inside here is proportional to the distance from the axis of the cylinder, and the axis of the cylinder is the z-axis. So you want to find the mass of E. This is a nice little problem. You know what to do. Let's see how you did. In cylindrical coordinates, the cylinder is r equal 1, and the paraboloid is z equal 1 minus r squared. So we can write E this way. E is the set of, in cylindrical requirements, theta runs from 0 to 2 pi, r runs from 0 to 1, and z runs from the top of the paraboloid up to 4, 1 minus r squared up to 4. And the density at x, y, z is proportional to the distance from the z-axis, so the density function ends up being k times the square root of x squared plus y squared, which is k times r. So the mass, as we learned before, is the triple integral over the solid k, and this is the square root of x squared plus y squared, but we already know that is kr. And remember here that dv becomes r dz dr d theta. Now I'm integrating with respect to z. Everything else is constant, and there's actually only a 1 there, so I'm integrating z. So when I integrate z and subtract it, when I integrate z, I will get z, and then I have the fundamental theorem of calculus is 4 minus 1 minus r squared. So this is the integration after I've done it with respect to z. I probably want to simplify this a bit before I do the integral with respect to dr, but I do it. And in fact, notice that one term depends on r, but there's no term depends on theta, and I can pull the k out. So this really is going to be the product of these two integrals. You should check this calculation because I'm going to ask you to do the calculation, but we get 12 pi k over 5 as an answer. Here's another problem for you just to evaluate. Now here you have to look at the geometry and think about what's going on carefully. And we're integrating x squared plus y squared. Again, this is pretty much tailor-made for cylindrical requirements. You know what to do. Let's see. This integrated integral is a triple integral over this solid. So x runs from -2 to 2. Y runs from minus the square root of 4 minus x squared to 4 minus x squared. And z runs from the square root of x squared plus y squared up to 2. And the projection of E onto the xy plane, you can see it here in the picture, is the disk. X squared plus y squared is less than or equal to 4. Now that's going to be a circle, so that means and you can see the symmetries with respect to the z-axis, so we can see that this is shaping up to be a nice application of cylindrical coordinates. Now, the lower surface of E is the cone, z equal the square root of x squared plus y squared. Its upper is 2. So this has a much simpler description in cylindrical requirements, coordinates, not requirements, coordinates. It's r, theta, z. Theta goes from 0 to 2 pi, r goes from 0 to 2, and z goes from r to 2. So we start with this integral, and we make the changes. Now, so what happens is we're using now e, so z, our first integral, goes from r to 2. Remember that dv becomes r dz dr d theta, so don't forget that. And this x squared plus y squared is really r squared. So then we just integrate first with respect to z. We don't see a z here, so when we integrate it, we get z, and we go from 2 to r. So this is what we get, 2 minus r, when we do the integral with respect to z. And now we have a case where these integrals actually are of different functions, so you can do them. This is the same thing you get for the iterated integral, and you'll get 16 pi over 5 for your answer. Make sure you can do calculations like this, because this is something I will assess you on. Also make sure that you can set up the integrals, because that's another important part in solving a problem of this nature. Let's do a final example. Find the volume of the solid that lies both within the cylinder, x squared plus y squared equals 4, and the sphere, x squared plus y squared plus z squared is equal to 9. You know what to do. Let's see how you did. Okay, so what happens is this is the picture that you should have drawn. And the projection of the inside of the cylinder onto the xy plane is shown here. So the volume of the integral is that z, and we just solve for z. We're going to do z, dz, dy, dx. So z is going to go from minus, I just solved for z here, so it is minus the square root of 9 minus x squared minus y squared, and I go to the top limit is the square root of 9 minus x squared minus y squared, and that is dz. But then because of this projection, I'm going to fix x. So when I fix x, y is going to go from the bottom of the circle to the top of the circle, so it goes from minus 4 minus x squared and square root of 4 minus x squared, and then x goes from minus 2 to 2 because of this projection. But that's really an awkward integral. It will be much easier to change it into polar coordinates. And so what you will notice that this is 9 minus r squared is what z is. And we also are going to see that, so z is going to go from 9 minus r squared to, from minus the square root of 9 minus r squared to that. So when you integrate that, that's just going to be 2, the square root of 9 minus r squared. And then this is r dr d theta. And here's that other r that we got because of the conversion to polar coordinates. dv becomes r dr d theta dz. So this is that factor of r that I get. And so now we're going to integrate r going from 0 to 2 and theta going from 0 to 2 pi. We do that calculation, and what we get is 4 thirds pi times 27 minus 5 to the 3/2. That is the exact answer. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.